All right, guys, we're going to talk about connected objects here. These are one of the more complex, I don't know if complex is the right word, more intense problems with a lot more steps than a lot of other force problems because we're dealing with multiple objects here. So what makes an object connected? Two objects are connected if they are forced to maintain a set distance between them. Okay? And if they do that, if they're forced to do that, they have the same velocity and they have the same acceleration. Now, that can happen because two objects are tied together. It can happen because two objects are literally just like pushing against each other. All right, we'll do one example of each of those. But the key here is that therefore that having the same acceleration. We're going to use that tool to figure out information about the problem. So, let's look at the first example. Find the force between the 3 and the 1 kilogram blocks. Okay, so we got this whole setup, 3 blocks in a row, and they're being pushed by 20 newtons. All right, so let's look at the individually at the 3 blocks, and then I'll show you an actual shortcut on this problem. But let's individually look at this kind of the long way. So a 3 kilogram block, what forces does it have on it? It has gravity, normal force, a 20 Newton push, and then it has some force from the 1 kilogram block. They're like pushing against each other. So this I'm going to call F31. 31. Okay. The 1 kilogram block, right? Normal force, gravity. It's got F31, and going back the other way, it's got F21. And then finally, we have the 2 kilogram block. Again, normal force. We've got, and just F21 going that way. Okay? All right, so we can set F net equations for all of these. We're not going to do the vertical part because the vertical part's always going to add up to 0. They're not like moving up and down. So normal force equals Fg, normal force equals Fg, like that's all we get out of it. But we can set up F net equations in the horizontal direction. So F net 3 is equal to 20 minus F31, right? Which means that 3a is equal to 20 minus 31. F net 2, or F net 1, I guess we'll do 1 next, is equal to F31 minus F21, which means that A is equal to F31 minus F21. And I want you to notice something here, right? These are the same accelerations, right? The whole idea is all 3 of these blocks have to have the same acceleration. So we can get away with just saying 1 acceleration for both of them. And finally, for the third one, we have F2 is equal just to F21, which means that 2a is equal to F21. Now, those 3 blocks, or those 3 equations, this one, this one, and this one, if they're set up properly and consistently, and you notice I did this direction was positive the whole time, if they're set up consistently, we can add them together and it will simplify. So I get 3a, and 2a, 6a is equal to 20 minus F31 plus F31 minus F21 plus F21. And I get that 6a is equal to 20, which means that acceleration is 6.67. Once I have that value, I can then go and find what each of these individual forces are. So I want to find the force between the 3 and the 1 kilogram block, right? I can do that by solving this equation right here. So 3a, this is not 6.67, sorry, 3.33, right, 3.33. I can plug that back into this equation, so this becomes 3 times 3.33 is equal to 20 minus F31. So 10 equals 20 minus F31. F31 equals 10. I could also find F21, and one way I could do it right here is this right here, F21. This is equal to, right, 6.67, and then and so forth, right? So I could find each of those ones by plugging back into those F net equations. Okay. This is a pretty common strategy. What you do on these problems is you set up the F net equations for each of them, and then you add them together to find the accelerations. Every connected object problem is done like that. So that's how you should start them all. Now, that's not true. Almost every one of them is done that way. Now, one little thing here. Notice the 6a equals 20. I could have just done that from the beginning. I could have treated this as if this was all one object with one force, 20 newtons on it. Mass of 6, and that would have given me the acceleration. But I'm still going to have to go back to those individual equations to find the individual forces. So if I just ask you the acceleration is 20 over 6. Could have done that from the very beginning. But if you have to find the individual values of the force between them, you're going to have those F-net equations. Okay, a slightly more complicated version. Determine the tension in the string. Now, the key to a problem like this where you got a pulley is you have to decide on a direction that's positive. And remember that pulleys change the direction of forces, of the tension in a string. But that also means it can change the direction of positivity. So I'm going to pick this direction to be positive. Okay, so down for the 3 kilogram block is positive, and up and to the right for the 5 kilogram block is positive. Okay, doesn't matter which way you pick, but you got to pick one that follows that string. So let's go ahead and look at each of the blocks now. We've got the 5 kilogram block. The forces on it are, I'm actually going to go ahead and split FG. So we've got FG parallel, FG perpendicular, tension, and normal force. Right? And so I could do the perpendicular direction is unnecessary. So I'm just going to do the parallel direction. F net parallel is going to be equal to tension minus FG parallel. And F net, the net force here, right, this is M times acceleration, right, because the acceleration is, actually I really should say 5 times the acceleration. Tension minus 5 times 9.8 times sine of 30, which is tension minus 24.5. Now look at this 3 kilogram block. 3 kilogram block, it's got upward force of tension and a downward force of gravity. So this becomes F net equals Fg minus tension. So this is 3a equals 3 times 9.8 minus tension. And again, we realize we add these two equations together, right? So I'm going to add the plus 5a equals t minus 24.5, right? I add those together, I get 8a is equal to 29.4 minus 24.5, okay, which means that a is equal to 4.9 over 8, which is 0.6125. Always finding the acceleration first. It's the easiest to find. So now we go back and we want to find tension. Easily done. I can plug it back into either equation. So let's do 5a. So I did 5a is equal to, right, t minus 24.5. 5 times 0.6125 is equal to t minus 24.5, right? And this comes out to be, what is it called? 27. So the total tension comes out to be 27.6 newtons. Okay? And that's how you find tension. And I should do it if I did the other equation. If I did 3 times 0.6125 equals 29.4 minus t, I should get the same tension this way. It turns out it's very, very slightly off, like 27.61 type off, right, because of rounding, but I get the same value. Okay. All right, one more example here. This is an object that looks like a connected object problem, but they're actually not connected. Here's why. You want to accelerate upward at 1 meters per second squared or 3 meters per second squared. Okay, what happens to the block in each case? So the block is sitting on the ground here. You're climbing the rope, right? So this person is going upward. All right. So that means it's not a connected object because the person is like, they're not at the staying the same distance apart. The person is moving on the string. So it's not really a connected object problem, but it's got a lot of similarities. So I wanted to go ahead and address it here, just so you can kind of see the differences. Okay, so person, right? What forces they have on them? Force of gravity, and they have the force of the tension, right? They're pulling, which means, right? Which is going to be the same as the tension. I pull down, tension pulls back up, same force. Okay, so I guess actually this should be, I'm pulling down on the rope, which means that tension, I'll just actually write just T. T is pulling up. Okay. Tension pulling up. So F net equals T minus Fg. In other words, I'm making that way positive. All right. Now notice, not a connected object problem. I don't have to go all the way around. So just for the person, up is positive. Okay, so I got 60A equals T minus Fg, right? I do this, I got 60 times 60 equals tension minus 60 times 9.8, right? This is, tension is equal to 648. Or, if we put 3 in here, if we put A equals 3, it would be 768, depending on which problem, right? So all I would have to do is put a 3 in there instead of a 1 to get each case. What about for the block, though? For the block, we have tension up, Fg down, and we also have a normal force potentially pushing it up. So F net, I'm going to do up again as positive here. Again, they're not connected, so I don't have to treat them as if they, like, I don't have to like switch the direction there. F net equals Fn plus T minus Fg. So let's say we're in the first case. So tension is equal to 648. Well, let's see what Fg is. Fg for this is 75 times 9.8. That's 735. So if the tension, the upward pull, is less than the gravitational pull, then A equals 0 for the block. It sits there. A is 0. We can even find normal force is just going to be the difference between those two, right? Because the normal force has to hold it up. So that's 52 plus 35. That's 87. But what if the tension, I should be like dividing this up. What if the tension is equal to 768? Now the object actually gets picked up off the ground, right? Because if the tension is greater than the force of gravity, it lifts off the ground. So F net is equal to T minus Fg. F net, I guess I should be saying that that is 75A is equal to 768 minus 735, 33. A is going to be equal to, whatever it is, 33 over 75, whatever that is. Okay, it's going to lift up. Notice that acceleration is different, right? From the this was the case where the acceleration for the person was 3 meters per second. Acceleration for the block is meters per second squared. The acceleration for the block is 33/75 meters per second squared. So I guess it's just over 0.5. Now, one thing to note here is be like, well, if the block is lifting up, how can the person still like pull down on it? So it actually doesn't matter in terms of force. For humans, it's actually harder to pull down on something that's moving down. Our arms just don't work as well that way. So the amount of force you might be able to apply in that situation is worse. But it's actually not it's not like the force's fault. If you had a machine that was applying a constant force to the rope, it would actually be able to climb up while the block is also being lifted up, okay, even though they're different amounts. All right, that's it. Have a good one.